In this tutorial, we're just going to solve a simple problem related to nucleation. I think we should have done this probably around week 8 or 9, but since we were covering other topics, I didn't touch or didn't even make an effort to solve this problem. So this is extremely a simple problem. You must know how to use the Microsoft Excel. So you might expect some questions in your final exam. Since you are writing your exam from your home, obviously you can sit in front of your computer, you can use your Excel, you can use Microsoft Excel to solve some problems. So this is a very good exercise problem. Yeah, so this is something I created based on the experimental data that we obtained from the lab. So this may not look like a textbook problem. So how to do that? So before solving the problem, so let's see like what's crystal nucleation is about. I think we already covered this. I think it's part 4 of the lab, I think. So we already talked about right. So we already talked about Gibbs free energy. So we all know what is a Gibbs free energy. I hope you remember this diagram, something like that. And then we already talked about the classical nucleation theory. So you cannot solve the problem if you don't know what Gibbs free energy is about and what classical nucleation theory is about. So if you think you are listening to this word for the first time, which means you didn't listen to part 4 of the virtual lab that I already uploaded in week 4 or 5. So try to watch that video and then come to this lecture. If not, you cannot solve the problem. So you must know some basic idea about what is Gibbs free energy, so what it relates. So obviously it's related to something like you start from a solution, your molecules they try to assemble into some stable nuclei, and the amount of energy that you need in order to, or this is something like there will be some energetic barrier, so for the molecules to assemble and then evolve into a stable nuclei. So that particular energetic barrier is something related to Gibbs free energy. Obviously it's a spontaneous process, so it will be, you will have some negative value. So which means nucleation is spontaneous. Even if you don't do anything, it's going to happen. So that's the meaning of that. And then we already talked about the classical nucleation theory. So, so classical nucleation theory have some parameter related to your Gibbs free energy. So you must listen to both of these lectures. If not, you are going to have a hard time in solving this problem. And then what we are going to do now is like we are going to use these two theories in order to get some parameters that we cannot easily obtained from the experiments, or there is no analytical technique that will allow you to get the parameters which you are going to calculate now using this theory. So the first parameter that you are going to calculate is surface free energy. And then once we have this parameter, we are going to calculate the Gibbs free energy. So Gibbs free energy. So there is no like an analytical probe. Like you perform some nucleation experiment, you put a probe, and then you can get this free energy from which you can get a Gibbs free energy. Sorry, I mean like there is no analytical probe that will allow you to calculate directly the surface free energy. So this is not something like a measurable quantity, but this is something we can predict using the theoretical knowledge that we have on the crystallization, or in particular nucleation. Yeah, so so that's the goal of this particular problem, and we all know what is a Gibbs free energy. So this will be my last lecture for this module, so try to pay some attention and spend some time on solving this problem. So what is this Gibbs free energy? So we all know this is something related to the stable volume or the surface, something related to stable volume plus stable surface. So in fact, it's a combination of both. So composed by molecules. So whether whatever the stable volume or stable surface that we are going to create inside the solution, obviously it's going to be composed by molecules, which should eventually evolve into stable nuclei. So whenever we think about Gibbs free energy, it's something related to stable nuclei. So that's what we are going to calculate. So the amount of energy that we need to overcome in order to create a stable nuclei from a solution. So obviously this is something like a molecular assembling process. Eventually they assemble into a perfect pattern and evolve into a stable nuclei. So this is what we covered in part 4 when we talked about Gibbs free energy and classical nucleation theory. You must listen to that lecture. It's because there I also explained how the stable surface changes with respect to radius, and how the stable volume factor it changes with respect to radius of this critical nuclei. And then normally you sum up this quantity in order to get the critical free energy. That's the amount of energy that you need to overcome in order to create a stable nuclei from the solution. So these are really pure theory, and then we are going to use this theory for the moment. And always remember, if your free energy is less than the critical free energy, the molecules cannot grow, so they will dissolve back into the solution. If it's more than the critical free energy, then obviously they will evolve into a stable nuclei, or if you want we can call it like the stable crystallite, which should evolve into a crystal. They might grow in the solution instead of dissolving back into the solution. So this is something that you should remember. And then what we are going to do now is we are going to perform a nucleation experiment, and then we are going to calculate the nucleation rate. So if you remember this classical nucleation theory, I already showed you in the other lectures. So let me write it here. Classical nucleation theory. This is very simple. Okay, before that we can write what is the critical free energy, delta G critical. So this is something related to 16 pi sigma cube v squared 3 kt ln of s the whole square. So this is the critical free energy. You already know what is that. And then we already discussed what is a classical nucleation theory, C and T. So J is equal to A exponential of minus delta G critical divided by KT. So this is your classical nucleation theory. So we already know what is delta G critical. So all we need is to just substitute exponential of minus 16 pi sigma cube v squared 3 kt ln of s the whole square multiplied by kt. So this is something surface free energy. This is something we are going to calculate now, or you can just say surface energy. And then this is the molecular volume of the crystallizing compound. So these are like a property of the molecule. If you take one molecule and then if you calculate the volume of that molecule, so that's very simple. And then so this is like a geometrical parameter. So if you take a molecule and then you calculate the volume of that molecule, so that's nothing but the molecular volume of that particular molecule. So this is something like a geometrical parameter. We don't have to measure anything. If you know the chemical structure, then we can easily calculate the molecular volume. So this is something like the volume occupied by the molecule in a space. Normally this is a very small number, somewhere in the range of 10 to the power of 28 meter cube. Very small number. Yeah. And then, so K is your Boltzmann constant. Boltzmann constant. Again, a very small number. And then T is your temperature. T is your temperature. You must learn these things, yeah, because you are in the pharmaceutical and industrial chemistry students, especially, they're going to use crystallization again and again for purification of API compounds. And if you get by chance like any job like crystallization scientist, they will ask you to measure solubility, they will ask you to perform nucleation studies and so on. So it is a must. What is nucleation is about, how to perform that experiment even, and then from that experiment how to calculate the nucleation rate, and then from there you also need to know how to calculate the Gibbs free energy and the surface free energy and so on. Yeah. So that's what we are going to do at the moment. So I will also show you how to do the experiment, and then how to get the result from that laboratory experiment, and then from there how to calculate the nucleation rate. And this J value, J is nothing but your nucleation rate. This is also a very tough parameter to get directly from the experiment. So this is nucleation rate is nothing but number of crystals, or maybe let's call it as nuclei formed per unit volume per unit time. So if you made say like 1 million nuclei, say like in 1 liter of your solution, say in 1 minute, so that will be your nucleation rate. So you have some solution, suddenly out of nowhere it's going to nucleate and form so many nuclei, and you have to calculate that number mathematically. So obviously we cannot put a probe to calculate accurately what will be the number of nuclei, what's the number of nuclei formed in that solution per unit time. But since we have that theoretical knowledge on what's a Gibbs free energy, what is a what is nucleation rate, we will calculate it. We will calculate this value analytically using some expressions. So that's what we are going to do. So in fact, we are going to use a probability function to calculate nucleation rate J value. And I will also tell why we are using a probability function instead of some normal expression, because nucleation itself is something related to your probability factor. Yeah, like probably that solution can nucleate or may not nucleate, something like that. So that's why we are going to use a probability function. So I think everything is fine. So J value, okay, I think this is good. So what we covered so far is like I just try to make remember or remind you what's the what this term the theory is about, like what's a Gibbs free energy, what's a classical nucleation theory, and what are the parameters involved in them. So I think everything looks fine. So what is this nucleation? So nucleation is something, I think we already covered this in the previous lecture. But anyway, I can quickly remind you. So one thing you have to remember: nucleation is like it's not a deterministic process. It's not a deterministic process. It is completely a stochastic process. Stochastic process. So why is that? I will show you the evidence from the experiment. So what is this? What does this mean? Is like imagine you all know how to perform a nucleation experiment. Like you take a say like you take some 20 ml vials, for example, or it can be a 2000 liters reactor, whatever. So you add some supersaturated solution. Let's say we have a supersaturated solution in all of these vials. Say supersaturation of 2.2, supersaturation ratio of 2.2. And then if you don't disturb these vials, if you leave the vials after some time, since your concentration is above the solubility concentration, the molecules will try to assemble, and then eventually they like to crystallize, or they how do you call it, they will tend to nucleate. So the molecules will come together, and then they will try to assemble into some perfect pattern, and once it's reached that critical free energy, they will form into a stable nuclei, which then eventually grows into full crystals. So I already explained this in the previous lectures. You have to watch my lectures on crystallization, and especially I have a separate lecture on Gibbs free energy and classical nucleation theory. You must listen to it. Only then you will understand. So what will happen is, like, let's say like we have a stopwatch, and then we are monitoring the time. And then if you sit and watch, what will happen is, like, say the first vial may nucleate at 2 minutes, the second vial may nucleate, say, like 2 hours, third vial may nucleate at, say, 20 minutes, and the fourth vial may nucleate even after 2 days. So for almost 2 days, the solution will remain in solution form. There will not be any nuclei or no solid phase in that solution. Everything will be completely dissolved state. So, but we start the experiment with the same solution that contains same solvent, same solute. Everything is maintained at same temperature. Your supersaturation ratio, everything is same, but still the the nucleation might happen at different time intervals. So that's why we call it as a stochastic process, because it's unpredictable. We cannot tell, like, okay, I'm going to take that particular supersaturated solution, I'm going to load it in a 20 ml vial, and then I'm going to say, like, after 1 hour and 1 minute it's going to nucleate. That's a no way. It's completely stochastic process. If you can do that, like after 1 minute it's going to nucleate, then it will become a deterministic process. So that's the difference between stochastic and deterministic processes. Yeah. So nucleation is a stochastic process, and if you want, we can say the probability, introduce the probability factor. Like, if you look at here, like, let's put one more vial here. Say again, we maintain the supersaturation of 2.2, and this time we are waiting for 20 days, and still we observe there is no formation of any solid phase. So practically there is no nucleation. So what does that mean is, like, the probability of the fifth vial to nucleate is almost zero. So that's the meaning of these things. Yeah? So everything is related to something like a probability. Okay, the probability of the first vial to nucleate in 2 minutes is more likely, and the probability of the say, like, the third vial to nucleate in 20 minutes is more likely, and so on. So this is more like a probability. Okay, probably this vial can nucleate. So if I start an experiment with 100 vials, it is probably all the 100 vials may nucleate, probably 50 percentage of my vials may nucleate, or probably all the vials may never nucleate. Yeah? So even if you wait for infinite amount of time. So this is something that you have to remember. So that's why we call it nucleation as a purely stochastic process. And I already said to you how we perform an experiment. So whatever I showed you with these 5 different vials, that's what we exactly do in the lab. We prepare some supersaturated solution, we put them in the vial, and then we will monitor the time it takes to nucleate. So this is something you have to to remember. And then what I'm going to show you is, like, some experiment that we did in the lab. So what we did is, like, we took a salicylic acid. It's an active pharmaceutical ingredient. This is widely they use to how do you call exfoliate your skin. So if you, how do you call, like, if you go to your pharmacy, if you ask for the card remover, like a band-aid, if you flip the card and if you check what's inside, it will be mostly salicylic acid. So it will try to help to remove the dry skins. So it is one of the most widely used active pharmaceutical ingredients, and we are going to crystallize them. We are going to crystallize that in ethyl acetate. So what we are going to do is, like, we are going to prepare a supersaturated solution, say, like a supersaturation of let me check what I used, I don't remember. Hmm. Okay, let's say like a supersaturation of 1.2. So we put some different vials. So we used like 40 vials. So we prepared a supersaturated solution of 1.2, and we prepared a 40 vials. So all of these vials contain the same solution. It contains salicylic acid, and your ethyl acetate is your solvent, and the the supersaturation ratio of the solution in all of these vials is 1.2. And then we are going to wait, sit and wait and watch when this solution is going to nucleate. So we are going to say like we have a watch, and then we have a lot of patience to sit in front of the experiment and watch how, but what time each of this vial nucleate. Say like this vial 4, it may nucleate at 2 minutes. Say this, the last vial may nucleate at 3 minutes, the first vial may nucleate at 40 minutes. So what we are going to worry is like we don't care, we don't have to even, we don't even need to label these vials. All we need to know is like there are 40 different vials. For example, you can even start the experiment with 100 vials, and then what we are going to do is like we are going to create a table like time, and then so let's my say like at 2 minutes my first vial nucleated. So time and then number of vials nucleated. So when time t equal to 2, say the first vial nucleated, and when time t equal to 3, the second vial nucleated. When time t equal to 4, so let's express time in terms of minutes. So third and fourth and fifth vial nucleated. And then when time t equal to 5, say like sixth, seventh vial nucleated. And then sixth, when time t equal to 6, not seventh vial, 7 vials nucleated. It can be, it can be any of those 40 vials. When time t is equal to 6 minutes, let's say some 8 vials got nucleated, and then so on. And say like when time t equal to 40 minutes, all the 40 vials nucleated. So all the 40 vials nucleated. So what we have here is something like we have some time, and then we have how many number of vials nucleated with respect to that time. From this one, we can calculate the probability function as a function of time. So what is this? The probability of nucleation. So let's call it as a probability of nucleation. You might watch this video 2 or 3 times to understand, I guess, because it's a tough concept. Even researchers or PhD students who are working in this area, they struggle at some time. So try to pay attention. You might expect some questions in the final exam. So what we are going to calculate is probability of time. So sorry, probability of nucleation, which is a function of time. So that's why I put the t in the bracket. So what is that? So if you look at here, the first vial, see at 2 minutes, one vial got nucleated. So what is the probability of one vial getting nucleated out of the 40 vials? So that will be roughly 1 divided by 40 multiplied by 100. And then if you come here, the last vial, when all the 40 vials get nucleated, when time t is equal to 40 minutes, so what is here? So this will be the probability of 40 vials getting nucleated at the 40th minute is 100 percentage. So how 40 vials got nucleated, and this is the total number of vials, so multiplied by 100. So that's, so what does this mean? Like at 40 minutes 100 percentage of the vials got nucleated. So that's the meaning of this. So what we have here is like we have something time. So this is something we can measure experimentally. We can even observe with our naked eye, and then we calculated how something called as a probability of your vials getting nucleated. So you have your time. So normally instead of time we call this as a TG. TG means growth time. Growth time. In fact, we don't even call this as like a time of nucleation. We call this as a growth time, TG, for a reason. If you listen to my lectures, I showed you how the molecules assemble to form into a stable crystallite. So if you have some molecules like that, they try to assemble, and then once the it reaches the delta G is greater than the delta G critical, they will evolve into a stable crystallite. and then these molecules, these crystallites will grow, or we can call them as a nuclei. Nuclei, or sometimes people call this word crystallite. So nuclei is the more correct word. So this, and normally this nuclei will be so tiny, and sometimes it may not be visible, but they tend to grow immediately, like they grow very fast. Or imagine if you have a solution, we have like so many millions and millions of this nuclei, then your solution will turn from clear to cloudy. So your solution will eventually grow from a clear solution to a cloudy solution. Sometimes we call this as a cloud point, or this TG. Sometimes we will even call it like a time to reach the cloud point. Not cloud point, maybe time when the solution become cloudy. When the solution become cloudy, or from clear to cloudy solution. If you observe your solution becoming cloudy at time t equal to 2 minutes, then that will be nothing but your growth time. So that's the meaning. So that's how we do the nucleation experiment, and that's how we check the probability of the nucleation. So as I said to you, nucleation is completely a stochastic process. So probably something can nucleate at some time, probably something can nucleate some other, the same solution can nucleate at some other time. So there is a high chances of getting nucleated, or not getting nucleated. So so this is something, a probability factor, and we have to capture the probability of that nucleation. So obviously we cannot capture the something stochastic by doing one single experiment. So that's why researchers, or anybody both in academia and also in industries, they always do several experiments. Say like they perform 100 experiments, and in that 100 experiment they check at what time the solution nucleated. So normally we do is say like so let's begin with say like 100 vials, 120 ml vials, and then we fill all the vials 20 ml solution of same supersaturation, and then we have to we can even put a camera, some camera, and then we can go to home. So camera will record at what time this solution nucleated. So we can replay the camera. So we can replay the movie which was recorded using a digital camera. From there we can get some values like time, and then the number of vials nucleated. So we can say like say 2 minutes, 3 minutes, and then say a 50 minute, 4 vials nucleated, and then until we have to monitor until all the 100 vials get nucleated, or 100 vials are nucleated. So that's the, so this way we almost captured the stochastic nature of the nucleation. So we know that say this is my system, say like for example salicylic acid dissolved in ethyl acetate. So I know the probability of 100 vials getting nucleated at that particular supersaturation is say like 1200 minutes, and then the probability of one vial getting nucleated at that particular supersaturation is say 2 minutes. So we captured the stochastic nature of this nucleation using a simple experiment. So and then in this type of experiment, the only observable is when the solution turns from clear to cloudy solution, and then we have to monitor the time, and then we can calculate the probability of your vials getting nucleated. So this is something like the say like which number of vial. So the let's say like vial number. So whenever I say vial number, it doesn't mean like you are labeling the vials. We don't even have to label the vials. So if the vial number is 6, means it's the sixth vial got nucleated at some particular instant of time, so and divided by the total number of vials multiplied by 100. So that will give the probability of that this many number of vials getting nucleated at that particular interval of time, say like 1200 minutes, say 90 vials got nucleated. So the probability of 90 vials getting nucleated will be just 90 by 1200 into multiplied by 100. Sorry. So whatever the value you get, so that meant that's the percentage of your vials getting nucleated. So something like 90, in this case it will be 90% vials getting nucleated. So that's the, sorry, this is wrong. We start with 100 vials, so probability of 90 vials getting nucleated will be 90 by 100 multiplied by 100. Obviously this is 90 percentage. So 1200 minutes, 90 percentage of your vials will nucleate, or so that's the meaning. So this is like a more like a probability. And this information, like if you manage to capture the stochastic nature of the nucleation with like a reliable number of experiments, from that we can calculate the nucleation is something related to like number of nuclei formed per unit volume per unit time. So this is extremely tough. Imagine like you have a solution. Out of that, nowhere this clear solution turned into cloudy solution because it got nucleated. So how do you count the number of nuclei in that solution? Obviously, this is not an easy, impossible task. In fact, yeah, with the level of analytical instruments that we have at the moment in the laboratories. So this is something you should keep it in the mind. So, but we will get this number mathematically once we manage to capture the stochastic nature of the time using a probability distribution function, which is given by, let me check one time, I don't want to do any mistake. So it's given by probability of your vials getting nucleated, which is a function of some time, is equal to 1 minus exponential of minus jv into t minus tg. Oh, sorry, I think I did a mistake in the before. So whenever I said this TG, this is just the time. So TG is something related to the time at which when your first vial got nucleated. First vial nucleated. So when you observe the first vial is getting nucleated, so that's the time, that's the growth time. So this is like a terminology. If you want, we can call it like a T of one vial, something like that. A T of first vial. So this is like a probability function. So what we are going to do is like the probability of the vials getting nucleated with respect to some time is something related to your nucleation rate, and then your volume of the reactor. So volume also plays a big role in the nucleation. Say like if you perform some experiment, say like 220 ml supersaturation so, sorry, the solution supersaturation say is 2.2, and if you perform the same experiment in a 2-liter reactor, and then say the supersaturation ratio is 2.2, everything is same, solution is same, temperature is same, but if you see the time at which the nucleation happens, it will differ. Normally in the smaller vials nucleation will be faster, and in the larger vials nucleation will be slower. So slower in the means it takes extra time. Say like if you observe the nucleation in 2 minutes, here you will observe the nucleation roughly in, say like after 2 days. So roughly like that. So volume also plays a big role when you perform a nucleation experiment. So I think so far so good. Yeah. So we if we have this if we capture the probability of your whilst probability of the nucleation experimentally, from that one we can calculate the nucleation rate. So what we have here, we have, let me write it here. So this is the probability of nucleation. So if we start with 100 experiments, still we can calculate this function. If we perform the experiment with the 20 vials, still we can get P of t. So 1 minus exponential. J is your nucleation rate. V is the, the volume of your solution. Say like we are performing the nucleation experiment with the 20 ml solution. And then T is the time at which each of your vials getting nucleated. So time of nucleation. And then this is the Tg is the time at which your first vial got nucleated. So I think this is fine. So these are some probability functions. So obviously there are many other ways to calculate nucleation rate. So I took the easiest one because this is a simple exponential function, and most of the time the data that we collect in the lab, it follows an exponential trend. So let me go back what we do in the lab. So as I said, if you start an experiment with the 20 vials, for example, supersaturation ratio of 1.2, say we did experiment at 20 vials, and then we are monitoring time versus number of vials nucleated. Say like you have say times 2 minutes, 3, 4, say like 5.5, say 7.5, 9.5, and then say 12 minute, 15, 16, 18, say 20, 22, and so on. So let's say at 2 minutes the first vial got nucleated, and third minute, say like two more vials got nucleated. It's not like the vial number, it's like a number of vials that which got nucleated. So which means 3 vials got nucleated when time t equal to 3, and say like 4 vials got nucleated when time t equal to 4, and when time t equal to 5.5, let's say 5, 6, 7. So 7 vials got nucleated in total. So this is something like a cumulative effect. So we are just counting how many vials got nucleated. So at 5.5 minutes, you will see 7 vials already have some crystals, or it's already got nucleated. So we will see how the nucleated vials will look like. I will add some video to this lecture. So from there you will get some idea. And then at 7.5, let's say 8 vials got nucleated, and 9.5, say, so 2 more vials got nucleated. So that will be 9 and 10. And then at 12 minutes, let's say 3 more vials got nucleated. So that will be 11, 12, 13. And say like at time 16, say like 4 more vials got nucleated. That will be 14, 15, 16, and 17. And then say like time 18, 2 more vials got nucleated, 18 and 20. So what does that mean? Like when time t equal to 18 minutes, so the probability, almost 100 percentage of the vials got nucleated. So now we can calculate the probability of nucleation. So this is very simple. So this is like 1 divided by 20 multiplied by 100. Here is 3 divided by 20 multiplied by 100. Here it will be 7 divided by 20 multiplied by 100. So this is like a percentage, like how the percentage of your vials getting nucleated, the percentage of the total number of, if you started with the 20 vials, so 7 by 20 multiplied by 100, so that's the percentage of vials which got nucleated if you started your experiment with the 20 vials. And then finally, when time t equal to 18, 20 vials will be nucleated. So all the vials will be nucleated. So that will be 20 by 20 multiplied by 100. So which means 100% of the vials are nucleated or encountered the nucleation. So far everything is fine. So 20 vials got. So this is like a. So this is something like we calculated the probability of nucleation. And now all we need to do is like we have to we have time we have time t, and then probability of nucleation. We got this from experiment. I will show you in the video how we do this experiment in the lab. It's not a tough experiment. It's very simple. It's time consuming, laborious, then but you need somebody who can do the experiment carefully. But it's a very simple experiment, and from there we can calculate. We can fit these two values in this function, which I already showed you. T minus Tg. So if you all you need is to fit this P of t versus t. Let me change the color. So all we need to do is like we are going to fit these two values. So we will get some graph like if you plot this value t and P of t, you will get something like that. T expressed in minutes, P of t. It will range from 0 to 1 or 0 to 100. It depends on how you express the probability. You can express in terms of percentage, or you can express without multiplying by 100. So in that case, probability will range from 0 to 1. 0 means no nucleation. 1 means all the vials got nucleated. 0 means no vials got nucleated. Point 0.5 means 50% of the vials got nucleated. And then if you plot this time versus probability, you will get some graph like that. So there will be 20 points here if you started with the 20 vials, and there will be 100 points here if you perform the nucleation experiment. If you try to capture the probability of nucleation using 100 vials, so you start the experiment with 100 vials. I know some people, they even go up to 500 vials to accurately capture the nucleation rate. So the more the number of vials, better you capture the probability of the nucleation. So better will be your nucleation rate, that value that which we calculate. So all we need to do is like we have to use this equation, and then we have to calculate this J value, the nucleation rate. And we have already Tg. If you take this experiment, if you go back to this table here, your Tg value is the time when the first vial got nucleated. So in this experiment, Tg will be 2 minutes. Tg will be 2 minutes. I hope you all follow up to this point. So what I'm going to do is like I will stop recording now, and then I will add a small clip of the experiment which we performed in the lab. That experiment was performed by Shubhangi. She's my friend, and now she's working in a pharmaceutical industry in Cork. So this is part of her PhD work. So she studied the nucleation of salicylic acid in ethyl acetate solvent. So ethyl acetate solvent, and she performed all the experiment with the 40 vials, I guess. And she prepared a supersaturated solution. So say like she did one set of experiment with 40 vials with a supersaturated solution of, say, I don't remember this number, say like 1.2, and then I will tell this number exactly when I add the video clip, and then another supersaturated solution of, say, 1.4, and then another 40 vials will be here, and then say one more experiment with a different supersaturated solution, and then another set of experiment with different supersaturated solution. So if you want to study the effect of initial supersaturation, say like a 1.2, 1.5, say 2, 2.2. So which means we have to perform 1, 2, 3, 4, 4 multiplied by 40 vials. So we have to perform that many number of experiments. So 40 vials in each experiment. So if you want to study, okay, my solution is supersaturation. Sorry, my solution supersaturation is 1.2, and what will be the probability of nucleation or the nucleation rate if you want to calculate? Then you have to do 40 vials, and then for is supersaturation of 1.5, and if I want to calculate the nucleation rate or if I want to calculate how the nucleation rate changes with respect to your supersaturation ratio, then we have to do this type of experiments, and then we have to perform 40 different we have to use the 40 different vials. From there we capture T versus P of T, and that from there we can calculate your nucleation rate. So eventually we can plot something like supersaturation, initial supersaturation versus J value, nucleation rate. So something like nuclei per unit volume per unit time, and this is supersaturation ratio. This has no unit. So you all remember the formula C by C star. Think this is fine. Maybe I will also explain here itself, like how to do the experiment in the lab.